So we have already seen the DB scan clustering, and we are in the way to see why DB scan clustering is actually being used. We know that DB scan clustering is actually used to as an outlier reduction technique and as one of the major replacement for K-means clustering. Why K-means clustering is not used? Why? Because it requires the K value to be specified as well as the initial cluster centers also to be specified. Next comes that any variation of K-means clustering is available or not. So that variation should be able to detect how outliers can be avoided in K-means clustering, or how we can actually project outliers separately in K-means itself. That's what the variation we are going to see, that actually called as K-medoids clustering technique. That's what we are going to discuss today. So this is actually one of the variation of K-means, which actually says that the normal algorithms, if it is a normal K-means algorithm, what it actually does, it actually takes some initial cluster center, a randomly picked initial cluster center based on the K value given, and and if that initial cluster center is highly biased, then it will not take into account of outliers. It will try to include all the points inside the clusters. It will not avoid any points that it is actually more wide from the initial cluster center. So we should avoid like that. It will not do anything. It will try to include all the points to the cluster. So that is what the major drawback that we find in K-means, that is outliers are not detected. So this K-means clustering technique, I'll write a sample definition here so you can understand it better. So it is a generalization of K-means where the K-means itself is done in iteration. Usually K-means by default is an iterative algorithm, where this K-medoids algorithm is actually a generalization where the K-means itself will be repeated several times. Instead of doing it in an iterative manner, it will be doing it in a generalized manner. Let us see this with an example problem also. So this K-mean clustering, we can say it is a partition-based clustering. So K-medoids is also going to be a partition-based, right? So let us see. It is a partitioning clustering algorithm, which is slightly modified from K-means, but highly complex. Highly complex in the sense it will take more time rather than on the same problem is solved using K-means. K-medoids algorithm is more robust compared to the normal K-means. But the problem is it will take more time for the algorithm to get converged. So let us see this with an example problem on how this K-medoids clustering will actually do, and we can understand what is actually medoid. We know mean is nothing but the centroid. For each iteration, I'll be calculating the centroid. I'll be updating the centroid each iteration, and I'll be doing the clustering process in K-means. Whereas here we have something called as medoid. So what is that medoid? So we will see it. A medoid is nothing but it is an object which tries to make everything as close as possible. A medoid can be defined as an object or a particular point in the space of points given to you, object of a cluster. That is any one point in your cluster, not necessarily the center point, any one point in your cluster whose average dissimilarity to all the other points will be as low as possible. This is actually the main thing. Dissimilarity to all the objects in the cluster is minimal. Say for example, the main difference what actually occurs here is, so the medoid is nothing but I cannot choose anything as an initial cluster center. If you choose anything as an initial cluster center also, it is not always the thing that the initial cluster center will always be in the correct position where all the points will correctly surround it. That will not be the case in K-means always. Surely there will be some points which is actually somewhat more further from that point, and since it is actually far more further, in any one cluster it will try to be getting fitted. Say for example, I'll show with some diagrams here and how that will actually look in K-means actually. Hope my drawing is visible, right? These things. This is visible, right? What I'm scribbling here.
Yes, sir.
Yes. So there will be some points here. That is actually the case in K-means. Then can you say what are the two clusters that will be formed with this? Can I say this as one particular cluster? A spherical cluster will be formed with this, and this alone will form a cluster. Assume that I have some points. Say here I have one point. I have one point over here, and how this point will be covered? This cluster will be increasing its length to somewhat, and it will try to cover this point to here. Am I right or wrong? In K-means clustering, I'll be having a particular point inserted into any one cluster, even though it is actually so wide from the entire distribution of data points. So this is actually the main drawback of K-means. Let's suppose if this is the cluster center, then what actually happens? This actually I term it as a medoid. Why? Because if you see the dissimilarity between other points, it will be very less. See, all the points are very close to this particular point. Hence, this particular point I can say it as medoid point. Similarly, for this particular thing, I can say this as a medoid. So I can if you take all the other points, then the medoid point will have some equidistance or actually near equidistance to all other points. That is, the distance to all other points will be as minimal as possible. So in this case, these particular points and all will not be getting that much evidence. Why? Because they may be sometime dropped. Why? Because an efficient medoid may not be available for this particular point. So they can be dropped. So that hence this K-means itself can be varied in such a way that an efficient medoid can be identified as initial cluster center. Instead of identifying a random initial cluster center, an efficient medoid should be identified as initial cluster center. This is actually the main concept of K-medoid cluster. In normal K-means, I'll be randomly giving you any two data points as initial cluster centers, and we'll be proceeding with the clustering processes. Whereas in K-medoid clustering, I'll not be selecting initial cluster center randomly, even though it is being selected randomly. Each time the clustering strength will be evaluated and seen how cost it is actually how much cost the clustering is actually incurring. If the cost is very high, it means that the clustering is not done at a good rate. I need to modify my clustering process. So what will happen? I need to change my initial cluster center to a better initial cluster center. So what is that better initial cluster center? The better initial cluster center will be a medoid center. It will be a medoid. What is medoid? Medoid is nothing but medoid is a point which is actually closer to all other points in the same cluster. So that is actually the thing. Now let me go into the problem, an initial problem. And as usual, since it is an MCQ kind of, let me solve the problem, and finally I'll be letting you know how different kind of small things can be asked over those problems. Okay. Let me give you a set of data points, and from those data points we are going to do a clustering process. Let us do K-medoid clustering over this data sample. Say I have set of 10 points. Yes. So these are the data points available for us to do the K-means clustering process or K-medoid clustering process. The thing to understand here is, here will be given how much, what is the K value, but we may not be given with the initial cluster center. Why? Because according to K-medoid, you can randomly select any one point as a medoid or the initial cluster center. So there is no thing that you need to be given with the initial cluster center. You can randomly take any one point as a initial cluster center. Or sometimes in the problem we can be given, and let's suppose here, since it is a first problem, let us assume that A is equal to 2, which will be given. Actually here also, since it is going to be a partition based clustering algorithm, it cannot be done without K value. So K value is given, and assume that, and let the initial cluster centers be, and we are assuming it, we are saying it let, so we are assuming it, then the developer also can make some changes over the initial cluster center. So I'm setting it to be 3, 4 and 7, 4. So these are the things we actually have. So for this particular data point, how we can actually proceed is, we can usually do the same process what we do for the K-means, and there is no much difference. I'll be calculating the distance between each and every point to 3 comma 4 and 7 comma 4, and I'll be finding how they are actually differing with respect to the distance. Say for example Euclidean or Manhattan or row distance metric or chi-square, any distance metric I'll be taking, and the closer thing I'll be assigning to a particular cluster, either C1 or C2. Next only whether I'll be able to judge whether 3 comma 4 and 7 comma 4 are a medoid or not. If they are not medoid, I need to go for a separate cluster, separate initial cluster centers. Yes. So let us proceed with this. Say for example, the initial cluster center is going to be 3 comma 4 and 7 comma 4, and this is 7 comma 4. This is for C2 and this is for C1, and what cluster it actually belongs to. So these are the things what we actually have. This is the thing. Let us find the using the Euclidean distance. So using Manhattan distance metric. Can anyone say the formula for Manhattan distance metric? Right. So let us actually calculate it directly because it is not that much difficult to calculate using the Manhattan. So this is actually sorry, this is actually not Manhattan, right? X2 minus x1 the whole square plus y2 minus y1 the whole square. Yes. Yes. So 1 minus 3 the whole square will be 16 plus 2, 4, 20. Am I right? Is it right for 3 comma 4 and 7 comma 6? Come on, why this much lull?
Correct, sir.
Yes, sir. Or I can use the Excel sheet itself. I have opened the Excel sheet. I can directly feed the formula over here. Equal to this is 7. Sorry, this is x minus 3 the whole square plus y minus 4 the whole square. Similarly here, x minus 7 the whole square plus 6 minus 4 the whole square. Yes. So let us see the interior clusters we will be usually taking, which is minimum, right? So this first point, point 1 belongs to which cluster? Point 1 belongs to
Second cluster.
C2.
C2. Next, C1,
C1, C1,
C1,
C2,
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 C1,
C1,
C2,
C2,
C2, C2, C1.
C2, C2, C1. Great. So with this is actually the process in K-means. We'll be iteratively doing the same thing again and again with respect to the K-means until the next class iteration is having the same cluster parameter with respect to the current thing. If it is like that, then we'll be doing then we'll be saying that yes, the thing has been converged. So we can actually say that the clustering is completed. That is with respect to K-means. But in K-medoid, it is slightly different where just a minute. Before going for the next iteration, we need to prove that the selected initial clusters 3, 4 and 7, 4 are good medoids. So what is medoids? This medoid is nothing but they are actually points which are actually closer to all other points in the same cluster. Say for example, if first 3, 4 is taken, all the clusters, all the points in the cluster C1 should be as close as possible to 3, 4. So let us actually verify that. Right? Verification of medoids for 3, 4 and 7, 4. So this is why I say K-medoid is going to be highly complex. Why? Because in K means we can directly select any one thing as initial cluster center and we can proceed for iterative process. But K-medoids, selecting initial cluster center is itself is a very difficult process. That itself will run for iterations. So what we have to do, we have to calculate the distances between the points in the same cluster one by one. So we know that this point, what are the points that belong to clusters 3, 4, right? So I'll be writing cluster 1, and what are the points that belong to cluster 1 is say 2, 6, 3, 8. If I miss anything, please help me. Okay, 3, 8. Next is 4, 7. Next is 3, 4. That actually the point that is directly taken. So we have 4, 7. 4, 7, 3, 4, 3, 8, and 2, 6. Am I left anything or am I correctly writing it? Correctly, right?
Correct.
Thank you. Yes. And cluster, okay, cluster 2 has more points. Okay, right. And in cluster 2, 7, 6, 1, 6, 8, 5. 7, 4, that is the point directly. 6, 4. And what is the point I missed? 6, 2 and 7, 3. Okay. 6, 2 and 7, 3. So these are the points. Next, what we have to do, we have in this cluster, what is the initial cluster center we have chosen? That alone you highlight. So the initial cluster center chosen is going to be 3, 4. And in this group, the cluster center chosen is going to be 7, 4. The thing is, yes, they are good enough to form a cluster. That is not an issue here. They are good. But whether this 3, 4 and 7, 4 are good to form the medoid or not, that is what we are going to check. Okay. The thing is, if you do K-means clustering, randomly any one mean will be taken as the initial cluster center or the final cluster center. That randomly that mean will may not be the one of the point in the given data sample. But in K-medoid, the center should be one of the point in the data sample. But in K means the center may not be the one of the point in the data sample, because each time I find the cluster mean, I'll be finding the centroid that will be taken as the center point. Okay, so that's so we are avoiding that in K-medoid. Okay, so this is one of the MCQs. You remember that, right? In K-medoid, the points that is taken as center will be one of the point in the data sample, whereas in K-mean, the point which is chosen as center will not be in the one of the point in the data sample, because it is a centroid point. It is calculated, right? Now we find it is that in that dissimilarity measure, right? Dissimilarity measure. It will be equal to these points. So from 3, 4, I need to find the distance. I already have the distances ready. So I'll go here and take the distances. I have the distance say 5, 6, 16. Here we are 10 and 0. 5, 16, 10. That 0 need not be taken because the distance to itself. So what are the distances? I can actually say the cost of 3, 4, 2, 6 plus cost of 3, 4, 3, 8. Next, cost of 3, 4, 4 comma 7. So these are the costs we have. So I know that the total cost is going to be the summation. I already have the distances, that is I mean the cost. So that is 5 plus 16 plus 10. I have 5 plus 16 plus 10. Right? Hope you understand how the costs are actually taken. You just see above the points represented there that actually represent the cost. Here the cost, if you take the distance between 3 comma 4 and 2 comma 6, you can recognize that the cost is going to be around 5, and that the 3 comma 4 to 3 comma 8 is going to be 16, and 3 comma 4 to 4 comma 7 is going to be 10. So that is what I'm taking it, right? Yes, am I making it clear?
Yes, sir.
Yes. Now what we have to do, the same process we have to do for that second cluster center with respect to 7 comma 4 also. So for 7 comma 4 also we can do the same thing, and what is the point that comes for 7 comma 4, we can write the same thing and we can enumerate in the initial cluster centers how much distance they have actually. So let us go and do that. This is dissimilarity cluster, or I can actually unite this in the same. This is for entire thing is for cluster 1, and for cluster 2 also the same thing I can do. So that is cost of 7 comma 6 comma 7 comma 4 is the center, so 7 comma 4 comma 7 comma 6 plus cost of 7 comma 4 comma 8 comma 5 plus cost of 7 comma 4 comma 6 comma 2 plus cost of 7 comma 4 comma 7 comma 1. Finally cost of 7 comma 4 comma 6 comma 4. These both things we actually take, and for this also I can find what is the cost. And I calculate both. This is 5 plus 16 plus 10 for cluster 1, and for cluster 2 I calculate the same thing. For cluster 2 it is 4 plus 2 plus 5, 4 plus 2 plus this 0 is not considered, 5 plus 1 plus 1, 4 plus is it right? Say I have written it correctly, right? I take the thing into consideration here. So the point will be now 5 plus 16 will be giving me 21, 31 over here. Plus 4 plus 2, 6 plus 5, 11, 13. So what is the total thing is 44. Am I right? It is 44, right?
Yes.
Yes. Now we are getting here cluster 4 as 44. Now, then what we can actually do is, now this particular initial cluster center, say 3, 4 and 7, 4 is giving you a dissimilarity measure of 44 when they are selected as medoids. Now, you have three other choices for 3, 4. What are the other choices is 2, 6, 3, 8 and 4, 7. And for here you have some other choices, say 6, 2, 7, 3, 6, 4, 8, 5, 7, 6. So now you can change the medoids one by one and find which is the better medoid here. You have to select it. So likewise, you have to change, given K, you have to find all possible items and find which is the better medoid. Right? Now, considering 7, 3 as medoid for C2. I'm going to consider 7, 3 as medoid to C2. What will happen? That is what I'm going to do. So repeat. So computing the distance metric. So the same thing need to be computed again. So instead of 7, 4, I'm going to take 7, 3 now. We'll go to the Excel. This is 7, 3 now. Any change in the clusters? C2, C1, C1, C2, C2, C1, C2, 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 and C1. No change in the clusters, I hope. Only thing what I can do is I can just copy this. I put it over here. Now you calculate this particular thing again. The same dissimilarity measure with respect to 7, 3 you have to take. For 7, 3 we have to take. So instead of 7, 4. So now instead of this initial cluster centers we have 9, 5, 1, 2, 2. So 9, 5, 1, 2, 2. 9, 5, 1, 2, 2. So 9 plus 5, 14, 15 and 19 I get. So what is the dissimilarity measure with what I get here is going to be around 50. So the medoid 7, 4 is better than the medoid 7, 3 or C2. So this is what the conclusions will be giving. So since it is actually going to be done in a pen and paper, I am actually taking that's any one thing and doing. But when you do in the system, you have to try all possible combinations for the K. All the possible K values you have to take and you have to do the computation process, everything. So that is with respect to the K-medoid. Since it is only using pen and paper, I am directly taking anything and then I am doing it. So not with much deviations. Right? I am making it clear. Am I making it clear?
Yes, sir.
Yes. So how we can ask these questions now? How outlier is actually detected here? Yes, the outlier will be detected if you see the dissimilarity over any one particular point which is selected as a final good medoid. So you'll be selecting medoids one by one, and finally you will be converging and selecting any one part to any two when k is equal to 2, any two as a best medoids. In that best medoid also, some points will have a higher distance. Say for here it is 16, and some points may have higher distance. Those points can be considered as an outlier points. So by this way, the K-medoid clustering can overcome the difficulties faced by K-means clustering with the same process with some generalizations. So K-medoid can be used for outlier detection also. Now, how can we use this for MCQs and stuff related to that? Now I ask you some questions. You have a note if needed, right? Whether the initial cluster center chosen in K-medoid will be the point in the data sample or not. I'm asking a question to you. I repeat the question. Whether the initial cluster center chosen by the K-medoid algorithm will be the point in the data sample or not.
Point in the data sample only, sir.
Yes, it will be the point in the data sample. Why? Because if I repeat again and again also, I'm not going to calculate the centroid or mean anything. I'm not going to calculate. Only one time I'm going to do, and then I'm not going to wait for any convergence results. My thing is to find the better medoid for the given sample. In K-means, it is not like that. I'll be finding something called as the centroid. I'm making it clear. This is the first thing I want to say you first note. Second, with respect to the iterative mechanism, whether K-medoid is going to follow iterations similar to K-means or not. Just like a true or false I'm asking. K-medoids is going to be following the exact iterative steps as K-means. True, false, depends upon the problem, none of the above like that. We have K-means. In K-means, what we will be doing? Initial cluster center will be there. At the end of iteration 1, I'll be taking the centroid. I'll be changing the initial cluster center. Then the new cluster center will come. Repeat the process. Again and again, you do the iterative process. Then if iteration 3 or something is having the cluster configurations, same as iteration 1, then I say that the clustering has been converged. So we can stop the iterative process. This is in K-means. Whether the same iterative process is followed in K-medoids or not. Say true or false alone. Great. It is not the exact iterative process. Then what is done here? Here we will be selecting the best medoid. I don't want any initial cluster. I'll be randomly selecting anything as initial cluster center, and I'll be shuffling between those initial cluster centers to find the best medoid. Now, what is medoid? This is also most important MCQ. Not only MCQ, most important definition also. When you go for a 2 mark anything. What is a medoid? The point which is actually closer to all the other points in the same cluster, to the cluster to which it belongs, right? If I ask you a question like this, if I put something like this, now can you say which is actually the best medoid for this? If initially this is selected, then we have to find which is the best medoid. Say quickly.
Center point.
The center point. We have to randomly select one by one. If you take this dissimilarity to this and this will be high, and one by one I'll be finding, and finally I'll be coming to this point. When I come to this point, I can find that the distance to all the other points from this particular point will be as low as possible. So this is the minimal thing I can find, and I can find this as the best medoid. And for this point, if all the points are having some smaller distance, and if any one point is alone having the highest distance, yes, this point is called as an outlier. Great. So this is actually the thing we have, right? So this is a vector medoid. Next, this medoid clustering, as I already said, it is a very time-consuming process because the initial cluster center itself is highly difficult. So what we actually have to do, we have to go for some other techniques, say Clara technique for doing this particular medoid clustering, right? Let us go and see the Clara clustering in the subsequent class. Okay. Yes.